Episode 108, Betelgeuse, Betelgeuse, Betelgeuse. And welcome back to another episode of the Syzygy podcast, joining you live. Well, not live. We're recording live. We're in Emily's office. Emily's looking at me strangely now.
How do you not record live?
What a bizarre. Well, I mean, it is. We're live, but they're not listening to us. Hello, listeners. Welcome to Syzygy. Emily and I are off to a great start here. We are in Emily's office, is my point. Sitting around the big round table in her office, still next to the big blank whiteboard. Emily, I don't know.
I'm so ashamed.
It's causing me unrest. But we're back for another edition of the Syzygy podcast, which is great. It's really nice to be back. And we're on a complete roll here. And to celebrate that, Emily, I've got something for you.
Woo-hoo.
You gave me a little gift a little while ago when you came back from an overseas conference.
I did.
So I've got a gift for you. It's present time.
This is going to become a regular thing. It's
Here
great.
we are.
Uh-oh. Oh, and beautiful wrapping paper.
Yes, I know.
All the way from Royal Mail. Oh, look at this. Oh, it's not one, but two Syzygy branded notebooks.
Spiral bound notebooks,
Excellent.
as requested, as
Yes.
demanded, can I say?
Well, as necessary, because I was just looking actually today, and I can only record 1, 2, 3 more episodes, and she's over.
Yeah. So they're not as thick as the ones that you've been using recently, but this is as good as I could do. These are from the Syzygy merch store. So listeners, if you want your own Syzygy branded spiral bound notebook or t-shirt or badge or socks or, there's loads of stuff, just go to our website, syzygy.fm, and follow the links to the store, and you too can be the proud owner of some Syzygy branded merch. So there we go.
And is that the Orion Nebula in the background?
I don't know. It just looks nice. You tell me. You're the astronomer. It could be.
Well, it's half cut off, so it's quite difficult.
I don't think it is the Orion, but it might be. Don't know. I'll have to look it up. But it is very pretty.
Well, if it is the Orion Nebula, it's a great way to segue into what we're going to be talking about today.
Well, we are going to jump straight in because we don't have any follow-up today.
No.
So we're leaping straight into something like we've been on a bit of a roll lately on topics that we've covered before. We've done, like last time we were talking about the biggest explosion ever, right? And we did that back in episode 61. But last time we did a big update to no. We need to go more in depth on really big explosions in the universe because we'd found another one which had, boat status, biggest of all time, brightest of all time. So this time we are recapping something that we have also talked about in the past, but we're going in more depth today. And that is the bizarreness of the star Betelgeuse.
Yes,
So
Betelgeuse.
can you remember when we talked about this last time?
Yeah, well, I do know because I looked it up when the last episode, if you like, was of Betelgeuse's weirdness, which was end of 2019. And I think we recorded early 2020 when this was still going on.
Okay, so going back a few years now, but like my memory of this is fairly hazy, but I do remember that Betelgeuse, big bright star in the sky, right, one of the bright ones, was going a bit weird. It was doing stuff. And the headlines that science journalists had scored from various astronomical papers and so on, reports, was, oh my goodness, Betelgeuse is about to explode. And all the astronomers went, no, that's not what we're saying. Just because the star is doing weird stuff doesn't mean it's about to explode. And so we put a bit of a damper on that back in 2020, right?
Yeah. So this was when Betelgeuse was going really faint.
Oh,
that was when that was all part of that whole exciting period where, I remember literally looking up and going, what happened to Betelgeuse? Where's it gone?
Weird.
It used to be there, and now it's just this tiny little thing. It was impressive.
But the idea being, if something that bright and that big, because it's a big star.
Oh,
right?
big is not even a good...
We'll get into that. But something that bright and that big, changing and varying by this much, like something weird's going on, right? And so therefore you make big leap, particularly if you're not an astronomer, but you're writing to sell papers with headlines, must mean that it's doing something really weird. It's going to explode. It's going to go supernova because it's a really good candidate to do that maybe. And no, turns out not. But that weirdness hasn't gone away. So bit of an update on that today. Emily, what's going on? Fill us in. Where do we start?
Well, it's a great place to start, actually, with what that last episode was all about, which was sort of pinned around the late 2019, early 2020, what's now called the Great Dimming event of Betelgeuse. I'm not kidding.
Yeah, okay.
It's great. It's the Great Dimming. And this is where Betelgeuse just completely plunged down in brightness for several months. And it took us quite a long time to sort of figure out, hang on, what's going on here? And we're going to come back to exactly what was going on.
Because that is a bit weird. I mean, normally when you talk about like these kinds of events, sudden changes, like I'm guessing normally that got a lot brighter. Something energetic just happened. Whereas the Great Dimming is sort of, well, something just stopped. Something just turned off then. What's going on? So that is a bit, it's almost the opposite of last week's episode, which was all about huge explosions. And this is, no, it just got dim and quiet. It's a bit weird.
Very weird. But then now, so fast forward another, 3 years on now since Betelgeuse did its Great Dimming, then we're now looking at Betelgeuse getting brighter, like really a lot brighter.
Really brighter.
Like possibly the brightest we've seen it in decades, if not centuries.
Okay.
And it's now getting brighter and dimmer, so it pulsates in brightness. It's getting brighter and dimmer twice as fast as it used to.
All right. There's a lot to unpack there, right? We've got Big Star, went through strange period about 3 years ago, is still going through weirdness and is now super bright, brighter than we've ever seen before. And so it's changed. It's changing. It's oscillating. It's doing stuff. And that's speeding up too.
Yeah.
So the big question there is, what's going on? So can we back up a little bit?
Yeah.
Tell us about Betelgeuse.
Yeah, so Betelgeuse it's one of the brightest stars that we can see with the naked eye in the sky. It's actually pretty well visible across both hemispheres, which is nice.
Handy.
Yeah, so it's
hello to all of our listeners in both hemispheres.
Indeed, you can see it. So constellation of Orion. Everyone loves Orion. There's loads and loads of local mythology about Orion. Basically, wherever you are in the world, probably the indigenous culture had something to say about the story behind the stars in Orion.
It is one of those really just one of those most obvious constellations in the night sky.
Or even asterisms or just groupings of stars.
Yeah.
So Orion has, in the kind of more Western Greek mythology, he's a hunter. He's got the very, very bright stars of Rigel and Betelgeuse, who sit on two kind of opposite corners of the hunter. Rigel being one of the biggest, brightest, bluest stars in the sky, and Betelgeuse being one of the biggest, brightest, reddest stars in the sky.
Okay. So what does that mean about the star itself? I mean, it's bright. It's in a really obvious place in the sky. You can find it really easily. So what about the star itself?
So it's very, very red and it's very, very big.
Okay.
So it's a red giant, which sounds I'm being a bit patronizing here, but no, that's actually what we call this class of star.
It does what it says on the tin.
Yes.
Yeah.
So rewind back to a few episodes ago when we did stellar evolution, we talked about red giant stars. So these are stars that have gone through their what we call main sequence lifetime, that period of their lives where they fuse hydrogen to helium, just like the sun is doing right now. It's in its kind of middle age, happily, merrily chugging along phase. When the hydrogen starts to run out, then all bets are off, basically.
Right. Okay.
And they start to do interesting things. So stars will become big and red, and this is because there's not enough hydrogen in the core to support that hydrogen fusion anymore, at least not at the rate that it used to. And so the stars start to do other things. Eventually they'll start to fuse helium. So what they turned the hydrogen into becomes now the fuel for the next set of fusion reactions. And when you're doing that, you're actually producing more and more energy than they used to, which causes the star to expand out. And the expansion causes the outer layers to cool because they're much more rarefied than they used to be.
It's expanded out. So, I mean, it's a fascinating thing. There's so many things going on here. You know, it's very easy. It's very tempting to describe it as the star wants to. The star needs to start burning other things
I'm all
for fuel.
For personification of stars.
Yeah.
It's helpful.
But, I mean, it doesn't want to, it doesn't need to. When it runs out of hydrogen, right, the thing that it's balancing forces against is gravity, and the gravity tries to, it just pushes in even harder. So when it runs out of hydrogen to fuse, the gravity pulls things in even harder, which heats up the core, until it reaches the point where the helium does start to fuse, at which point it pushes back again because there's lots more energy coming out. So that's what we mean when we say it wants to, it tries to. But are you saying that there's more energy then coming out when it's doing helium, which sort of pushes out even harder?
Yeah, it's kind of one of these mind-bending things. It's hotter on the inside but cooler on the outside than it used to be, and a lot bigger.
So that's why it blows up to this much bigger. How much bigger are we talking about?
Well, in Betelgeuse's case, it's incredibly large. Betelgeuse's radius, we're not exactly sure what it is. We think it's somewhere between 700 and 900 times the radius of the sun.
Holy cow, that's really quite big.
Yeah. Which is it's pretty much most of the way to Jupiter in our solar system.
Oh, like I was about to ask you, so does that, like, how big is that? Does that get us out to like Mercury, Venus, Jupiter?
Jupiter.
Okay. It's like I'm way off. That's really big, Emily.
Yeah, it's more than 4 times the distance of Earth to the sun.
Really big star. Yeah.
It's
No wonder
it's
the outside's
monster.
a bit cooler. Yeah.
It's an absolute monster. So we don't know. It's one of these ironic things. Betelgeuse is one of the closer stars, in the grand scheme of things. It's relatively close to us in our galaxy, and we can do wonderful things with it because of that. For example, we can actually resolve the disk of the star.
Right. You can actually, like, it's not a dot anymore.
Yeah.
You can actually see it as a
We can see
disk.
it as like maybe there's a darker bit there and a brighter bit there and things like that.
How many stars can we do that with? It can't be many.
Very few, yeah, on the order of hundreds.
Because they have to be really close
yeah.
and really big to
Yes.
be able to do that, right?
Yeah.
Yeah.
So best measurements, which were actually made following up on the last dimming. So the last dimming and subsequent measurements have told us a lot about this star. And the best measurements that we have of things like the mass, the radius, particularly the age of Betelgeuse or its evolutionary point, come from astroseismology. Mm-hmm. So, super personal plug here.
You should see the smile on Emily's face when she says, I get to drop astroseismology in.
I know. And I get to drop in some of my favourite colleagues in here as well because they did some fabulous work on Betelgeuse at the time as well. So this is the work of Meredith Joyce and a few other astroseismologists. And they looked at Betelgeuse and they were able to determine some of these things much more precisely than we had before based on pulsation work and based on some wonderful stellar modelling as well. So anyway, we're looking at, so it's as I come back to this irony of being such a quite close star, we still have massive uncertainties as to exactly what the mass might be, exactly what the radius, like that's a pretty big error bar that I gave you, right? 700 to 900.
Yeah, that's pretty big.
Yeah, the mass is maybe somewhere between 16 to 20 times the mass of the sun.
Would that be the case for any star though? Like, is it that we have these models, we have an understanding of stars, of how stars work, and we know that, stars of this kind of mass would look like this, and stars of this kind of mass and this kind of age would look like this. But for any given star, like they're really far away. It's really hard to actually get information about any given star. Would that be right? Or is Betelgeuse a bit weird in that regard?
Well, actually, Betelgeuse is weird. It's one of these, it depends is the answer to your question.
Okay.
It depends.
Okay.
It depends on the star. Some stars we can get mass, age, radius, etc. crazily precisely, like down to the 5-10% level, maybe even 2% for some wonderful stars. And again, that's mostly astroseismology that's doing that.
Just a plug there.
Yeah. But those are only particular stars that we have very good measurements, well understand their pulsation mechanisms, well understand their evolutionary paths, etc. The typical garden star, we can get down to sort of 10-20% measurements is fairly typical.
Okay.
Obviously, the closer it is, then the easier it is to get more information about the star. You can get better spectroscopy, you can get better measurements.
Yeah.
So it's a kind of a bit easier. And then the further away it is, the harder it gets. So your errors get larger. But Betelgeuse is kind of in contrary to both of those, because although it's a pulsating star, it's at this phase of its life where there's so much uncertainty in what it's actually doing. It's in the final throes of being one of these large red giants, and it's got episoidal mass loss, so its mass is actually changing as you get loss off the surface. It's what do you even count as the surface is kind of an undefined question. Yeah, exactly. So it's doing all these kind of weird I guess, typical things.
Right, which makes it very difficult to then understand. So how big and how old and how massive is this?
Yeah.
Is this thing? Like if it was leading up to this point, you could say, well, we know what this star is like and we know what it's doing and we know where it's going to go. But when you're in the middle of that weirdness, it's really difficult to know exactly what you're looking at. Okay, that makes sense.
And these phases of a star's lifetime are pretty short in the grand scheme of things. And that means two things. It means that we can't find a lot of stars out there that are in this phase because effectively we humans are looking at a snapshot of the universe, right?
A really short one.
Yeah, exactly. We've only been observing these kind of stars for a couple of 100 years, let's say, with precision instruments. And so how do you talk about an evolutionary process that lasts hundreds of thousands of years or millions of years? Well, you don't. You don't observe that for a single star. You have to go out and say, well, that one's at that point and that one's at that point. So maybe you can connect the dots.
Right. Yeah.
But for the shortest phases, there's many, many fewer stars at that phase to actually study. So they become a bit more question mark. What's going on there?
That makes sense. You're trying to sort of extrapolate from much smaller amounts of data, and that leads to much bigger error bars. That
Exactly.
makes sense. Sure.
Yeah. So Betelgeuse is one of those. It's in the final throes, which is a very short period in a star's lifetime. So maybe a few 100,000 years at most.
So you're right. I mean, the irony of it being close and really big to the point where we can actually see it as a disk. But it's still too weird for us to really understand.
Exactly.
Okay.
Yeah.
So that gives us an idea about Betelgeuse. But tell us a bit more about what's been going on since the last time we looked at it. There was the great dimming, but what's been happening since? Like, why is this back in the news again now?
Yeah, well, Betelgeuse is a long-known variable star.
Okay.
It's one of the first known variable stars in terms of at least Western science, and there's some pretty good evidence now that suggests that ancient cultures, including Aboriginal cultures, knew that Betelgeuse changed in brightness hundreds and thousands of years ago.
Wow. I mean, that's got to be a fairly significant amount of change if, with the naked eye, you're looking at it and going, that's not as bright as it was, or that's brighter now than it was a while ago, like within living memory, or at least, within storytelling memory,
Well, it's even shorter than that because the brightness is kind of around about 400 days.
Wow. Okay.
For Betelgeuse typically. So you're talking about, just kind of over a year.
Yeah. Even so, that's some pretty good observation. But then again, I guess before Netflix, there wasn't much else. Like
people were very observant.
Yeah.
Right? And it formed a whole lot of cultural mythology about why things were going brighter and dimmer, and different cultures had different stories behind all that. And there's some fascinating ones that we don't have time to really go into all the details, but we can put some links up to some of the wonderful
let's do that.
Evidence
put them in the show notes.
Ancient people's understanding Betelgeuse. So one of the first known variable stars, because it has varied in brightness pretty regularly, pretty large variation for a pretty long time.
Okay.
Now, most of that variation is now understood to be what's called a radial pulsation.
All right. As in and out.
Yep.
Right.
Yep. So the whole radius of the star kind of changes, which changes its overall brightness over this 400-ish day period. And we understand that to be driven by what's called the Kappa mechanism or opacity mechanism. It kind of means you've got energy that's trying to escape the core of the star, right? The core of the star is doing all the fusion. There's lots of energy, lots of photons coming out. But there are particular zones in the star which are at a particular set of temperatures and pressures that mean that it's actually the opacities get really high, which means photons get blocked. They come into a resistive area of the star, and that causes them to build up. So you get the kind of this buildup of almost photon pressure behind that zone. It pushes the whole radius of the star out.
Like inflating like a balloon.
Yeah.
Right.
Yeah, the star then gets more rarefied. It cools down a little bit. It becomes more transparent to the photons. The photons all escape, and then gravity then pulls it gently back in.
And repeat cycle.
Yeah.
Okay.
So the actual kind of nuclear sort of chemistry behind all that's a little bit subtle, but that's broadly kind of what's going on when you get these
so
radial
that's your
pulsations.
sort of roughly 400 day, like call it a bit over a year. That's that kind of cycle. Is this sort of pulsing in and out, almost breathing.
Exactly. Yeah. So, Betelgeuse has been known to do that for a very long time.
Okay.
Then we had the Great Dimming event. And the Great Dimming event, as we saw the brightness that we see from Earth of Betelgeuse just plummeted. It was crazy times, because often you can sort of look at Betelgeuse and Rigel. You can see Rigel's a little bit brighter, but not hugely. And you can kind of say, oh, yeah, they're the parts of Orion. They're the bits that you recognize along with the three stars in the middle. But as a fainter red star, I was really searching. I was like, well, it didn't go away, but I was confused.
It got dimmer.
It got a lot
noticeably dimmer. And so what happened?
Well, we understand that to be something to do with a surface mass ejection. So a whole lot of stuff came off the surface of Betelgeuse and kind of like a big cloud. Mm-hmm. And then when that material left the surface of Betelgeuse, it cooled down even more. It formed molecules. It kind of became a big, dusty, black kind of cloud. And it blocked our view of Betelgeuse.
Okay, so it sort of sloughed off a layer, which then obscured it from us.
Yeah, and it seemed to have been a clumpy sort of layer, kind of happened to be in the direction of between Earth and Betelgeuse.
Right, okay.
So the sort of clumpy mess just kind of got in the way.
All right, so that's explainable.
Yeah,
cool.
Yeah. And then that over time, since that event, and mostly over 2019 into 2020, then since then Betelgeuse has been coming back to normal. That we think that cloud has been kind of dissipating or moving on in its life, and Betelgeuse has been slowly brightening up again. Interesting thing is that from that dimming period onwards, Betelgeuse wasn't brightening and dimming at 400 days anymore. It was doing it at 200 days.
So it's sped up.
Yeah,
as a
doubled
as a result of
in speed.
As a result of like losing that skin.
Well, we think it's all part of the same story.
Okay.
And that's what the paper is that kind of triggered all this coming through in different news articles and so on. So the paper itself is by Morgan McLeod et al. From the Center for Astrophysics, Harvard Smithsonian, that kind of team.
Okay.
And they were looking at, okay, how do we explain the fact that you've got this dimming and then the period's doubled, and then it's also getting really, really bright now, which is...
And to be clear, the brightness isn't just that the clouds have passed. Like it's not like the sun coming out behind the clouds on a cloudy day. This is the intrinsic brightness of the star itself.
It appears to be, yeah.
Right.
So, I mean, we're late May. I think our record measurement is somewhere around the end of April. It got really, really bright. And I can give you some numbers to kind of...
Sure.
Of course, we're talking about bright, dim. So Betelgeuse, we assign a brightness to the stars in the sky based on something called the magnitude scale. It's one of these things in astronomy. It's a hangover from long ago.
It made sense to someone at some point, and we still use it.
Exactly. Yeah. So it's a logarithmic scale, which means it's not kind of, you don't double in brightness for every double in number. It's one of those weird ones.
Right. Yeah.
But we and it's also backwards. Just for fun.
It sounds like a really bad scale, but let's go with it. You astronomers are happy with it, or at least you're resigned to it. So
it has elements. I mean, I'll defend it a little bit. I'll defend the backwardness of it, let's say, because at least the backwardness I think I understand. So what happened was somebody at some point decided, okay, we'll pick the brightest star in the sky and we'll call that 0.
Okay.
All right, because nothing's going to get brighter than that star. We're not going to discover more and more stars that are brighter than that star.
All right, so there's your baseline.
Yeah,
we'll call that 0.
Mm-hmm. And they chose Vega, which is not the brightest star in the sky, but they chose that
but
one.
It seemed like a good idea. Sure.
And Vega's also not quite 0. But anyway,
yep,
roughly.
The idea was good.
Yeah, and then, as we discover more and more stars with telescopes, et cetera, then you can carry on going up. You can always add more numbers that are higher, but you can't go backwards.
Okay, that makes it. Like if you'd said Vega is 10, right? And then you got dimmer and dimmer and dimmer and dimmer and dimmer. Eventually you have to go, oh, there's one even dimmer than that. And now we're into -1 and -2 and -3. And that's just complicated. So start at 0 and then as it gets dimmer, we go up in number. Is that what you're saying?
That was the concept.
Okay, yeah. I can see the reasoning.
Yeah, unfortunately it didn't pan out because although Vega is close to 0, there are stars that are brighter. So Sirius is a negative number.
And so you're going negative anyway.
Anyway, moving on from that. So we have these numbers. So Betelgeuse is known to vary from, it's sort of average, if you like. It's just, is about 0.5. Mm-hmm. It's a bright star. And it was known to vary from about 0 to 1.6.
Okay. And sorry, can I just interrupt? Is this brightness, is this perceived brightness to us here on Earth, or is this intrinsic, this is how much energy it's spitting out?
This is just the brightness we observe in the sky here on Earth.
So it doesn't make any sense to ask how bright is the sun on this scale?
Oh, it's like minus 20 something.
Right, but that's just because it's like really big and it's right there.
Right,
yeah. Okay, right.
So this is a logarithmic scale. So that kind of that variation between 0 and 1.6, let's say, that's a variation of about 1.3 times in terms of brightness.
Okay.
So but during the Great Dimming, it went from the Great Dimming to the point now is much more than that. It's about 3.6 times.
Right.
So it's from when it was dimmest to about now. It's now about 3.5 times brighter than it used to be. Yeah. Yeah. Exactly. So that kind of gives you a sense of the brightness change. It's significant. Now you can also talk about brightness of stars in terms of the chart toppers.
Yeah. Okay. This is sort of going back in the direction of last week. The boats.
Yeah.
In terms of star brightness.
Yeah, I mean, we sort of hold a list in our heads, if you like, of the brightest stars in the sky. And impressively, Betelgeuse has gone from being the 10th brightest star to being now the 7th.
Right, it's moved up the charts with a bullet.
Yeah.
Okay. Which, again, that sounds like a pretty significant change.
Exactly. So it's overtaken Achernar and Procyon, if you're watching those ones.
If you're keeping track at home.
And right now, it's pretty much on par with Rigel. So if it gets any brighter, it'll actually outshine Rigel, which is fascinating, I think.
It's a lot. Incidentally, it's interesting that all of these really bright stars, for fairly obvious reasons, they all actually have names. Like you're not talking about stars which are BX 5980Q, the other astronomical names that we so often come across on this podcast. These are stars with names, and presumably that's because they're the big bright ones.
They are.
And so we gave them names.
I think we talked about the names, and at least my notes said that we talked about the names back in the previous episode we did on Betelgeuse.
I think we might have, yeah.
So we talked about the Arabic origins of most of at least the stars that do have names in the sky. Origins, they're not all exact Arabic matches these days. I think you can spell Betelgeuse in 7 different ways, depending on how you want to translate it. But however. Anyway, so it's moved from number 10 to number 7. To number 7, yeah, and it may well become number 6 soon.
Goodness, okay.
So, yeah, amazing that just within the space of a few years, like not even a human lifetime, we can go out there, look at the night sky and have seen, well, Betelgeuse is really a lot fainter than Rigel. Hang on, Betelgeuse is now a whole lot brighter than Rigel. Isn't that weird?
So, and I mean, as you say, it's like this is really short period of time. Lifespan of a star, really long time. Like this is nothing. Like what is the lifetime of a star like Betelgeuse?
Well, we think it's going to have a couple of 100,000 years if it's lucky, actually. Right. Maybe a bit less than that, maybe about 100,000 years left.
But how long has it been going?
Oh, that's a good question. I can't remember what the original mass of Betelgeuse was, but it's going to be on the order of maybe 1 billion years, maybe a few hundred million.
So 3 years is literally a rounding error. So that's quite extraordinary.
Yeah.
So we just keep coming back around to, Emily, what's going on with Betelgeuse? What is happening here? And the question that everyone wants answered is, are we about to see this thing go kablooey?
Right. Let's answer the first question first.
Okay.
What's going on?
Because
that's exactly what the paper, as I promised, is talking about. So the idea is there has been this mode switching which has gone on in Betelgeuse, based on a whole series of events that's happened, which has also caused the Great Dimming.
Okay.
So the sequence goes something like this. We had an unusually large hot blob.
Okay. Is that the official term?
It is actually. It's in the paper. Yeah.
Okay.
Hot blob.
Hot blob.
You weren't expecting that answer.
I wasn't.
But the paper's actually, it's a wonderfully written paper. It's just one of these ones that uses really nice language to describe things.
Call it like it's here, like you see it.
Why
it's
not?
a hot blob.
Yeah, it's great. So in the surface of these very big red giants, we have a lot of convection. And convection is the bulk motion of parcels of hot and cold material. So the hot stuff rises, the cold stuff sinks.
Sure, just like hot and cold air in a room.
Yeah.
Circulating around.
And you get these sort of big parcels. And so lots of convection means lots of bulk motion of material. And that's one way that the energy can be transported from the inside of the star to the outside.
Okay.
So lots of convection going on. And if you have an unusually large hot blob of rising material in this convective zone, then it can actually cause a bit of a shock to go through the system of the star. So, I mean, we're looking at something that's a significant chunk of the radius of the star coming up through it. That shock was able to push a whole bunch of material off the surface of the star.
Okay.
It was expelled.
So that's what caused the dimming.
That's what then cooled down, formed the dusty molecules, etc., that formed the cloud that then blocked our view of Betelgeuse and therefore caused it to dim. So what we think is that this hot blob had another effect inside the atmosphere of the star, and that it broke the coherence of the pulsation that was going on.
Okay,
so it's radial pulsation.
This is that 400-day pulsation, in and out, breathing in and out, pretty regular for a really long time. We broke it.
Yeah.
I don't say we didn't do it,
The
but
hot
it
blob,
broke.
The hot blob broke it, right. So you got the surface, which was carrying on expanding. So if you have the surface, whatever the surface of the star means, carrying on outwards. So that's still expanding. But the deeper layers started to contract. Now, those two things should have been doing the same things at the same time.
Okay.
Right? But then they sort of switched so that they were doing opposite things at the same time.
I can see how that would cause some problems.
Well, what that does is it sets up a particular zone or a particular imaginary line inside the star, imaginary surface inside the star called a node. Mm-hmm. And the node is the bit that doesn't move.
Okay. So on one side of the node, stuff's moving in. On the other side of the node, stuff's moving out. And on the node, it's like, no,
nothing's moving.
We're the bit that's not going anywhere.
Exactly. And this is perhaps familiar to people who work with music. This comes across a lot because this moves the pulsation from what's known as the fundamental mode to the first overtone.
Oh, yeah. So if you play a stringed instrument, these are your harmonics on a guitar, for example. Mm-hmm. Yeah, okay.
Yeah, so a guitar string, for example, it's pinned down at two ends, right? If you use your finger to pin it down in the middle, you've gone from the fundamental mode of that string to the first overtone.
Right, and so you've got a node in the middle there where you've got string moving on one side of it, string moving on the other side of it, but that bit where your finger is just touching lightly right in the middle of the string, it's not going anywhere. That's your node. And you've just changed the note of the string by a whole octave. You've doubled the frequency.
Exactly. So you've doubled the period, well, in this case, half the period of the pulsation. So it now goes for 200 days instead of 400.
400, right. Someone's just done a harmonic on this star.
Yeah,
that's
exactly.
cool.
It's very cool, isn't it? So it's not a coincidence that he's gone from this wonderful round number of 400 to 200. It's halved for a reason.
Nice one. So this whole process of big hot blob causes big dust cloud that made us see it go dim, right? But that blob has caused the star to go into a different kind of oscillation. Mm-hmm. It's now doing something different.
Yeah, it's basically just pulsating twice as fast as it used to.
Yeah.
And now we think that this is not going to carry on for a long time, even maybe 5 to 10 years, because that whole convective motion, that's bigger than the motion that's going on in terms of the pulsation at this point. So the bubbles are moving kind of at a higher velocity than the actual pulsation velocity inside the star. So that's going to cause what we call damping, or it's going to kind of wash out eventually this whole pulsation, and you'll go back to the fundamental pulsation, the 400-day.
You're sloshing around too much stuff. That's not a stable oscillation.
Not when you got the big blobs going through it as well.
That makes sense.
Exactly. So that's quite exciting. So we're going to see this kind of 200 day period for perhaps maybe 5, maybe 10 years.
That's cool. And then eventually that'll sort of die out. Well, do we think that'll happen quickly, or will it just slowly fade out and you'll get the 400 taking over again?
It's a good question. I think there'll probably be a slow fade, but there'll be, I guess there's a point at which we won't be able to detect that frequency is kind of fading out.
Yeah.
Yeah.
So do we see this sort of thing happen a lot? Do astroseismologists looking at stars and how they wobble, do they see these kinds of shifts, and really over quite short periods of time, shifts from one mode to another, doubling of frequencies or halvings of frequencies? Like, has that come up a lot?
Not a lot, but we have seen it before. So that's mode switching. We have seen it in at least two red giants before. One is R Doradus, which was studied quite intensively 1950s to 1970s. That appeared to do the same sort of thing and switch back. And a couple of others we've seen switch back as well from their first overtone back to their fundamental mode. And so we think, this is probably just a thing that red giant stars do.
And presumably because they are so big, the outer parts of it, it's so diffuse, it's so spread out. You've got these enormous bulk motions of stuff, I'm guessing, that it's just somewhat easier to get changes in modes. It's easier to sort of pluck these harmonics, as it were, because it's so big.
Yeah, you don't get such a massive amount of convection in a pulsating star typically.
Right.
So it's when you've got this huge amount of convection and then the instability of causing these hot blobs that sort of break things up again. So it's the mixture of irregularity, huge amount of convection, that seems to be the trigger for these particular types of stars.
Okay, so that seems to explain quite a lot about what's going on with Betelgeuse at the moment. That big question of what is going on with this crazy star. Does it explain everything? Have we now nailed Betelgeuse down?
I wouldn't say that.
Okay.
Well, there's a lot we don't know about Betelgeuse. There are some very interesting questions that each of them on their own probably could have been a whole episode.
Right. Okay. Well, do you want to just hint at a few of them? Because I have a feeling that we're probably going to, in another 30 episodes, we'll be back on Betelgeuse again because it's just doing crazy stuff.
Well, like I mentioned, we don't know the basic parameters. How are we going to find out those? We think it's maybe got some kind of irregular surface. This is even pointing in that direction, but how do we measure that?
How do you mean irregular? What do you mean by that? Like it's spiky?
Well, hot, cold spots,
fur?
Maybe. Different bits have different temperatures. Okay. There's different bits of breaking of different parts of the convection.
I mean, something that big, it wouldn't surprise me.
No. But it's just weird. It seems to have, we don't really understand very well its magnetic fields. They're difficult to measure.
Well, as we've addressed before on this podcast, magnetic fields are hard anyway. Magnetic fields over that kind of size of star, that's going to break your brain.
Yeah. There's some evidence to suggest that in human history, Betelgeuse has changed colour.
Right.
It may have used to have been yellow or more yellow than it is now. Now it's very red. So that's an interesting thing. We would like to know, perhaps, this is the big one, I think, was Betelgeuse a binary star at some point in its life?
Is there evidence for that?
There's some ideas. There's some bits about Betelgeuse that seems to be rotating incredibly quickly, maybe too fast.
So could it got a big fling from what's like swallowing its binary partner?
Well, that's one option. Did it eat its binary companion, or did it get kicked off? Or
right. So, it having been a binary is a potential explanation for some weird stuff about okay.
Yeah, it's travelling at a stupid rate of knots through its local part of the galaxy.
Right. Something happened.
Yeah.
Wow, okay.
So, the masses of unresolved questions.
Okay.
And I guess the big one that everyone wants to know, when's it going to blow?
Yeah, because, let's back up a little bit. That's not just a random question. It is reaching the end of its life. Like you said, it's got something like maybe, a couple of 100,000 years left of in the order of 1 billion years lifetime. So it's really in those last phases. That's nothing.
It's nothing.
But it doesn't mean it's going to happen tomorrow.
No.
There's quite a large amount of time It could happen within, as far as humans are concerned.
Absolutely. Yeah. I mean, people have been quoting 10,000 to 100,000 years for a long time.
Okay.
And because basically those numbers don't change even when
no.
time advances by 20 years.
A long time is a very small amount of time in the lifetime.
Indeed.
Of a star.
So the first thing we need to address is, I mean, there's a lot of this thrown out whenever you talk about astronomy. Could it have exploded already?
Okay. Right.
So
would you...
yeah.
Red giant really could have exploded already?
Well, I mean, this is the idea that things are very far away, therefore it takes time for the light to travel to us.
Not in the sense of we can see it as a red giant now, and so at some time in the past to get to that point it could have exploded, but rather, are we about to see that it's exploded any day now? Okay, sure. There's that whole weird thing about when is now in the universe.
Exactly. So the light that we receive from Betelgeuse actually left Betelgeuse maybe around about 550-ish years ago.
Because it's 550-ish light years away.
Exactly.
That's how that works.
Yeah. So maybe 200 years ago it exploded and we're just waiting.
Sure. Okay.
That's incredibly unlikely.
I mean, we talked about this not long ago, that what are the odds that this would happen at the time when we happen to have the ability to look at it really closely.
Exactly.
So, it could happen, but it's very unlikely statistically.
And indeed, yeah. And it seems like Betelgeuse is kind of, it's still got a little ways to go, let's say, in its evolution. And that's what came out of the dimming event, and particularly Meredith's paper about measuring the pulsations and measuring the fact that it looks, or modelling the fact that it looks like Betelgeuse is still in this helium fusion phase of its life.
Okay.
Which that's the kind of the longest period of the last throes, if you like. Helium fusion is, and then you have subsequent episodes after that. So you can go into fusing higher and higher order elements before you get the big bang.
Yeah, I mean, the gravity will drag it down, and it'll keep ramping up those fusion reactions until there's nothing left to fuse, at which point all hell breaks loose. But those last phases, like how long are we talking about between, we've run out of hydrogen, quick, let's do helium, through to we've got nothing left?
Well, helium, you're looking at at least tens of thousands of years.
Okay.
And I guess that's where this 100,000 years comes from. And then they get progressively shorter and shorter the further you go up the periodic table. So I think you get a few years out of, say, carbon, nitrogen, silicon. You end up with only kind of a couple of days worth of fusion out of it because it just gets faster and faster and faster. Right. There's less and less fuel to get through. So everything happens quite quickly, even on human time scales.
It's like the star is just panicking. It's like, just throw this at it. We've got some silicon. Just throw it in there. And at the very last point, it's run out of fuel. And at that point, it's like a star of this size. What then like supernova? Is that what we're talking about?
It is supernova, yep. Right. So Betelgeuse is definitely big enough to do what we call type 2 supernova.
And just remind us, what does that involve? What happens?
Wow. So that's when, in short, basically the star can't hold itself up against gravity anymore. So the whole core is sitting there and it's getting compressed by gravity. There's more and more compression coming on, pushing it smaller and smaller. But there are limits to that. You can't compact matter infinitely dense. There are strict limits.
There are rules here.
Yeah, exactly. Yeah. And eventually you get to the point where you end up with just a little ball of neutrons in the center that you can't compress. And at that point you get, first of all, an implosion of the infalling layers of the star, and then they bounce off this neutron ball in the center and they explode.
Right. That's the big explodey part.
The big supernova
is once you make this really, really dense core of neutrons, then everything else falling onto it just goes bang off of that and explodes outwards ludicrously energetically.
Indeed, yeah.
I think we've established you don't want to be anywhere near that.
So it's a huge supernova.
Yeah. So as we're approaching that, like what you said a minute ago is that Betelgeuse still seems to be in maybe the helium burning phase, which could go on for a very long time in our lifespan. But are there signals and signs that we know of this thing is about to go supernova, or have we just we don't have that kind of data? We don't know. Are there things that you would look for?
It's interesting. So there's a couple of ways you can answer that question. So the first way is if you were just staring at a star that was literally about to go, could you tell it was about to go?
I guess that's my question.
So the answer to that is actually no.
Right.
Because there is not enough time for information about what is going on in the core to travel out to the surface at this point.
Wow. Like that's a really bizarre statement, which I think I'm going to need you to explain because like it's traveling at the speed of light, isn't it?
Well, not quite.
No?
I mean, my sort of canonical example is you take a photon that's produced in the center of the sun, right? Photon that's produced in a fusion reaction in the center of the sun takes an average of 100,000 years to reach the surface.
Okay. I do remember us talking about this before, and that still breaks my brain because like the sun's big, but it's not that big. It's not that that's the amount of time that it takes the photon to travel that distance at the speed of light. But what's going on is it's getting absorbed and re-emitted and bouncing around.
Yeah,
basically.
exactly. Yeah, so it can only travel a particular distance before it gets absorbed again, and then it's re-emitted, but it's not necessarily re-emitted in the original direction it was going.
So how long did you say?
About 100,000 years.
So all of this stuff could be happening down in the center of this star that we're looking at, which is about to explode, but we wouldn't know because the information wouldn't get out to us.
Well, yeah, so the only thing we can observe is the surface, so that's all we can tell.
I mean, that is just nuts. Like, I get it. I understand it. I can figure that out logically, but it still makes no sense. Like, that's mad. Okay.
So, but we do have another mechanism which we can say for sure whether or not a supernova has happened.
Well, you see a big explosion, would you?
Well, but even in the case of Betelgeuse, if we would know very definitively if it had gone to a supernova because we would see neutrinos.
Ah, you mean, so we're looking in the direction of Betelgeuse. We can't see a big explosion yet, but there's this other sign, which is neutrinos. Explain.
Yes. So while the photons will take a while to get to us, the neutrinos don't really understand that the rest of the universe exists.
Okay. So just to be clear, neutrinos, right? Neutrinos, tiny, really, really, really almost massless. They are tiny, tiny particles. And they're emitted from certain nuclear reactions. And there's a lot of them flinging around in the cores of stars because they come out of nuclear reactions, right? But the thing about neutrinos is they only see those kinds of nuclear reactions. They have no charge.
Nope.
So they don't see positive and negative electric charges. They don't bounce off things in the same way or get absorbed by things in the same way that photons would. They just, like there's huge numbers of them just whistling through us right now and going right through the Earth without even batting an eyelid. And so with a massive explosion like a supernova, you'd have just ridiculous numbers of neutrinos being flung out, but they would immediately leave the star.
Yes. Yeah.
And we'd see that.
So, yeah, we would see it. I mean, we'd still have to wait your 550 years.
Sure.
They still travel at the speed of light, but they travel...
Or slightly less because they've got a little bit of mass. But yeah, close enough.
Yeah. So they travel close to the speed of light. So we would see them approximately 550 years after the explosion, but they travel direct is the point.
Right.
And we've had very sensitive neutrino detectors switched on Earth for... I don't know, a few decades now, I guess 30, 40 years at least. Yeah. So we would see what's estimated to be something like 100 trillion extra neutrinos should Betelgeuse have gone supernova.
Something just happened.
Yeah, exactly.
As we said, I think, again, last episode, anytime you talk about trillions, that's a sign something just happened. Yeah.
Now, we wouldn't detect all those, but we would certainly detect, whoa, hang on, what was that?
We just saw 3 neutrinos. What just happened? Yeah.
Yeah, exactly. So we would definitely know from the neutrinos if it happened kind of, say, 500 whatever years ago.
That would be a big sign to say, point your telescopes up there because we might see something soon.
Yeah. Now, the other thing that would start to get quite exciting would be we would eventually see the brightening, right? And this is where everyone gets excited because you think, is it dangerous?
Because it's very close to us.
Is Betelgeuse going to be so bright we're all going to be blinded by the light? It's going to outshine the sun, or the neutrinos are going to fly through us and radiate us and we're all going to die.
It's the end of the world as we know it.
Okay. The neutrinos are not anywhere near enough to cause
any
kind of neutrino
I think
poisoning.
if you're going to die from neutrinos, there's probably other problems coming your way.
Yeah, no, there's not enough to do any sort of damage to humans and their neutrinos. Brightness-wise, you're probably looking at something about a quarter the brightness of a crescent moon.
Okay, so that's bright, but it's not bright. It's not going to light up the sky.
No, I'm not really frightened of something that's about a quarter of
the brightness of a crescent moon.
Or maybe I just drew a crescent moon. Maybe a quarter of brightness of the moon. Let's be generous.
Okay, so I mean, that would look cool. To be clear, we would notice.
Oh yeah, you would notice.
That's a really big, bright thing in the sky.
Yeah.
But we're not going to be able to read by it.
No.
No.
I mean, and we're not going to be irradiated and kind of start turning into X-rays or whatever it is that comic books, have when you have big supernova near you.
This is not super nasty Death Star in the sky.
No, and it would last for kind of maybe 3 months.
Yeah.
And then it would just kind of fade away.
I mean, it'd be cool. I can understand why people are interested in this.
Very exciting.
This is we're not downplaying this in any way, shape or form. We're just not going to die, is what you're saying.
Exactly. Yeah. No chance of dying from a star that is about a quarter of the brightness of the moon. Sorry.
How close would a star have to be before we would start sweating? You said this is 550 light years-ish away.
Yeah.
Like, are we talking tens of light years? 100? Like, how close?
I think it's on the order of about tens. Yeah, definitely Alpha Cen or Proxima Centauri, our closest star, if that did a supernova, we'd be in trouble.
We'd be in trouble, okay. And remind me?
That's about 3 light years away.
Light years away, okay.
Yeah.
Okay.
So
we've got a bit of a buffer there. We're okay.
Yeah, we've got a couple, 500 to 3. It's quite a big difference.
Yeah, good.
Yeah. And then finally, we would eventually, about 100,000 years after Betelgeuse exploded, we would get the shockwave reach us on Earth.
That's entertaining. What would that be then?
Not much.
Okay. Yeah. But what is it? Like, what's...
It's just kind of like that would be kind of the pulse, if you like, that's just traveling through the shock that's traveling through
the interstellar medium to get to us.
Yeah.
Through the vacuum of space, which is not a vacuum, as we've established before. There's some stuff there,
it's not a material shock. It's kind of the photon shock that comes through.
Okay.
And so, and that would probably just be deflected by there'd be a whole lot of charged particles coming through, and we've got a magnetic field and an atmosphere, so those charged particles would just bounce off us, basically.
Again, nothing to be worried about. Might cause some interesting aurorae?
Possibly. I'm not even sure if there's enough for that, to be quite honest.
Yeah, compared to the solar wind, not much.
No.
Yeah. Because by that point, I mean, remember this is going out in all directions. It's not like Betelgeuse is aiming it at us.
No.
Like a beam. It's like all directions. We're not special. And so by the time it gets to us, we're just one tiny dot. Yeah. Wow. Cool. Okay.
So that's about it.
Understandable that people are interested in this, right? This would be a really cool event to be able to go out and go, hey, kids, look, this just happened. Look at it. But we're not expecting this to happen tomorrow.
Astronomers would be so overjoyed.
They would go nuts.
Because we would get to observe this thing from a safe distance, but close enough that we could actually make brilliant measurements of it. I mean, when you do actually talk about the other stars that are even more likely to go supernova than Betelgeuse, I think we've got 2 other very clear candidates.
Okay. Yeah.
We've got Eta Carina, very, very famous nebula star that's really unstable, that seems to be about to go. Another one called Rho Cassiopeia, which is in the constellation of Cassiopeia, the big W in the northern hemisphere. So those 2 are sort of, I guess, higher up the most likely to go supernova list.
Right.
Still not talking about kind of next week scales. We still are talking about tens of thousands of years, most likely.
Well, I mean, surely there's no, like, over these kinds of time periods, like the uncertainty in that surely has to be thousands, if not tens of thousands of years.
Yeah, definitely.
There's no way that you could pin that down to, we think it's going to happen in 2025.
No. I mean, it's possible.
Sure.
It will happen very, very soon. The thing is with both of those stars is that they're 8,000 and 9,000 light years away, respectively.
Right. That's a lot further. That's an order of magnitude or more, almost 20 times as far. It's a lot.
Yeah. So they're not going to be as spectacular as Betelgeuse in that sense because they're a lot further away.
So put this on your astronomer's wish list, I guess, is the point here.
Absolutely.
It's why whenever this comes up, you like the excitement of, wow, if that happened, filters through to the headlines, and the headlines go, it's about to go. No, it's not. It's not about to.
No, it's not about to, but it would be so cool if it did.
It would be awesome. Hey, Emily, I've just had a thought. Do you know, do astronomers bet on this? Like, are there odds on this?
There's probably better things to put your money against. I mean, the number of years between now and 100,000 years from now. I mean, if you imagine that as kind of what do you call it in the casinos where you have all the numbers and you put your money on one of
like roulette, that kind of thing.
The roulette wheel.
This would be like a roulette wheel except with like 20,000 spaces on it.
Yeah.
And I'm now going to put
100,000.
I'm going to now put a cheeky 50 on number 2023. Yeah, okay. Yeah, fair enough. I think the problem there is that astronomers are probably a bit too numerate to be sucked in by that. Yeah. Fair enough.
But we're human enough to really want it.
That's right. Not so numerate that it's like, would it be cool? It'd be cool if it happened, but too numerate to actually put a cheeky 50 on it. That makes a lot of sense. Listeners, if you want to get in touch, Emily, how would they do that?
Well, the first thing you would do is go to our website, syzygy.fm, and you would go to the contacts page and you would write us a lovely, lovely message there, as have some other listeners this week.
Yeah, we got an email this week, which I was talking to Emily about it before we started, and I think we've got an episode there.
Oh, it's brilliant.
We do. So
it's
we won't
really
say
good.
any more about that right now, but just watch this space. There is an episode coming based on listener question, which is always exciting. So stay tuned for that one. Yeah, at the website there is a contact form.
Yes.
There is also what?
Oh, you can get all the past episodes. And here I would direct you to episode number 56, which I guess if you thought about it, we're episode 108, right?
We are.
So we're in the first overtone of episode 56, which was the original Betelgeuse episode.
Wouldn't that be 112?
Turns out I can't do maths either.
It
would be nearly the first
What were we
overtone.
saying before about astronomers being numerate? Yeah, it's almost.
nearly.
Almost. To within error bars.
Yeah, sure.
Yeah. Close enough.
Man, that's really annoying. I thought I had a great one there.
Do you know what it might mean, though? It might mean that in 4 episodes' time, we have to do Betelgeuse again because we will have seen it'll have exploded.
Possibly. Yes. But you can see other episodes in our back catalogue as well.
Other episodes are available.
Yeah, other ones you might find useful, such as Stellar Revolution, where Emily gets the numbers right.
Oh, dear. We are also on the Instagrams at SyzygyPod. We're on Facebook. Just do the search bar thing. And listen, if you want to support the show, there's a bunch of ways you can do that. Tell everyone you know that we exist. Tell them to go and find us and tune in. Give us a couple of stars. Give us a review to help us rise up through the noise of the podcasting universe. That's the best way to support us. But if you want to fling some money our way, go to patreon.com/syzygypod to help us keep the show running, the electrons flowing through the website, and to do the thing that we love to do. And speaking of the thing we love to do, we'll be back again for another episode sometime really soon, Emily.
Yes, we're going to do it. And I'm going to start my new notebook very soon. I've got to complete the old one.
You do have to complete the old one,
Yeah.
but that's all right. You've got a couple of new notebooks there. And we've got to put something up on the whiteboard. This is really important. I'm losing sleep over this one. Listen, everyone, we'll catch up with you at the next episode. Until then, Emily, see you later.
See you later.
Bye, everybody.